Go! So we're going to pick up where we left off on Friday. You did most of the first half of this slideshow on your own Friday. We'll use it as a little review. We'll talk about the fancy calculus speak that identifies all the stuff you did on Friday. We'll review a little bit, and then we'll get into some more excitement. You'll recall, way back when we started talking about derivatives, I said the derivative of a function is responsible for three things. We talked about one of them, which is the slope of the tangent line. We're going to get the other two today. Oh, exciting times, my children. Woo. Yep. So, what are we going to do? Well, we are going to start by talking about the constant rule. What is the derivative of a constant? For instance, what's the derivative of 7?
0.
0. Why?
Because 7 to the, what is it, 0 power?
Yeah,
No.
7 times 0 is...
Yeah, 7 times 0 is 0.
So one way you could look at it is 7 is 7x to the 0 power, bring that down.
Yeah.
Right? What's the graph of 7 look like?
So,
Yeah.
horizontal line.
Horizontal line. What's the slope of a horizontal line? 0. Beautiful. We talked about the power rule. This is what we did on Friday. We'll come back to this. This is just that you should be able to. Okay. X to the nth, taking the derivative of that, getting nx to the n minus 1. Constant multiple rule. What if we put a constant in front of a function? 7x squared. Well, we did that. Bring the exponent down, multiply it by the number in front, reduce the exponent by 1. Easy peasy lemon squeezy. Sum and difference rule. The derivative of a sum is the sum of the derivative. The derivative of a difference is the difference of the derivative. You'll notice what's missing, however, is product and quotient. When we did limits, we talked about product and quotient. Derivatives have different rules. What does that mean? That means that the derivative of A times B is not the derivative of A times the derivative of B. There's an entirely different function, or a rule, I should say, that we'll get to later. Today, we're just doing sum and differences. And you've done that already. We did something like the derivative of 3x squared plus 2x minus 7. That's a sum and a difference. You can do that. We will talk about trig, your favorite. And then we'll also talk about rate of change, which is the second part of the properties of a derivative. Okay. First one, slope of the tangent line. Second one, rate of change. The third one, your friend and mine, Mr. Physics, gracias, is velocity. Is it safe to assume that you've all had or are currently taking physics?
Yeah.
Yes. Is it safe to assume you love it to death?
Now,
Yes.
Excellent. Good. Glad to hear it. We do things a little bit different than physics, but I'll show you what we do differently when we get to it. All of that wraps up into one nice little slideshow. The first couple of slides I'm going to go through quickly because we've done it already and you are by now already establishing yourself as masters. Constant rule. Excuse me. If we have a constant, f of x equals c, you take the derivative, you get 0. Okay, we did that already. And, have you ever heard the expression beat a dead horse?
Yeah.
What does it mean? Beat a dead horse. Thanks, Einstein. What does it come from? What does it mean? You just use expressions you don't know what they mean?
It's pointless.
It's pointless. The horse is already dead. You can beat it. It ain't going to run any faster. Same thing is true here. What's the derivative of 7? What's the derivative of 0? What's the derivative of -3?
0.
You see the horse being beaten right now, yes? Okay. The last one, however, is worth mentioning. What's the derivative of pi squared?
0.
Pi squared.
All the time.
Isn't it just pi? 2 pi. Wait.
Bring the exponent down, reduce it by 1, 2 pi. Just 2 pi, right?
Yeah.
No, it's 0.
What?
All of it, dude. Pi's and numbers.
Why is it 0?
Pi's and
I
numbers.
don't forget.
Go ahead. Yeah, it's just a constant. Pi is still a constant. E is a constant. You all know E, right?
Oh, my bad.
2.1, 1828, 1828, 459.045. You have that memorized out to like 12 decimal places, right?
Yes.
Well, you will later. Power rule we've done already. There it is. By the way, I included here capital letters, the color red, and flashing. to try and drive the point home. Okay? Do you get it?
No.
Okay, good. Let me do it again.
Now I got it.
Okay, good. The only thing I didn't include, which I failed you as a teacher, is I didn't put it in a blue box. Because anything in a blue box for us, I mean, is the most important. This is pretty important, because we're going to be doing it for like 3 months. But again, we did this on Friday. You told me this rule, and we applied it. And we're going to apply it some more. Like when we do this. What's the derivative of x cubed? 3x squared, hot diggity. What's the derivative? Ooh, we ramped up quickly. What's the derivative of the cubic root of x? You think so, Mr. Smarty Pants? Give it to us. What do you got?
It's a guess.
It's a guess.
Yeah.
All right, go ahead. We'll take a guess.
It'd just be 1/3.
Nope.
Nah, try it.
It's a good guess. Anybody else? Go ahead.
Is it 1/3 of x to the negative 2/3?
Woo! Yes, it is. Well done. The cubic root of x is the same thing as x to the 1/3. Then apply the rule. Bring the exponent down, reduce it by 1. 1/3 minus 1 is negative 2/3. The last step, you don't necessarily need at this point in time. You will eventually, but I'm more concerned if you can just get the derivative. We'll worry about cleaning it up later, getting rid of those negative exponents. What's the derivative of 1 over x squared?
Negative 2x to negative 3.
Well done. And again, if you want to clean it up, you can move the negative 3 down to the bottom, but we can leave it like that also. Well done. Constant multiple rule, this is boring. Okay, great, there they all are. I just took functions that we've done already, put constants in front of it. You can write all that down. Got it? Good, let's move on. This is more funner. Yeah, well, I mean, you're using it already. If there's a number in front of it, you just multiply it. Or you can do the derivative and then multiply by the number later. You understand what I mean by that? Well, here, I'll clarify. Hold on. So let's suppose I have a function, 7x squared, and I want to take the derivative. I can do that 2 ways. I can apply the rule that we've learned already, and that is 2 times 7 is 14, subtract the exponent by 1 and get x. Or I could write this as 7 times the function x squared. Take the derivative of x squared, which is? 2x. And they would get 7 times 2x, which is 14x. Oh, look, same. I don't care which one you want to do. I would suggest that we're going to do the first one more because it's a lot quicker. But that's what the constant rule says. We've been doing this already also. We did that when we took the derivative of polynomials on Friday. The derivative of 3x squared plus 2x minus 7 is the derivative of 3x squared plus the derivative of whatever I said second, plus the derivative of that constant, which I forgot also because I'm like a goldfish. What's the derivative of that function?
3x squared
3x squared minus 4. That's it. Where'd the 5 go? It disappears, right? It's magic. There we go. Good. That one's a little hard to read. That's over a half, but okay, we get that. That's not real exciting. Oh, here we go. Way back when I said I am not a big fan of memorization. This is something that you're just going to have to memorize because I don't have any clever way for you to remember it, and it does cause problems. Let me give it to you first. The derivative of sine is cosine. Well, that's easy. The derivative of cosine is negative sine. That's easy too. But what you're going to do at some point in time is you're going to forget where that minus sign goes. And it's going to haunt you. And again, I wish I had a clever way for you to remember which is which, but I don't. Derivative of sine is cosine. Derivative of cosine is negative sine. Okay, what's the derivative of 2 times sine x? 2 cosine x. What's the derivative of 1/2 sine x? 1/2 cosine x. What's the derivative of x plus cosine x? Now we get the sum rule going in there. Take the derivative of x, which is? Derivative of x, which is 1. The derivative of cosine is negative sine, and therefore we're left with 1 minus sine x. Everything we do from this point on just takes these basic ideas and makes them more complicated. What about the derivative of tangent? What if instead of the sine of x, we're taking a derivative of sine of x cubed? What if we take the derivative of the sine of x cubed over the tangent of x squared? Ooh, that'll be fun. That's all we do for the next 2 months. Not really all we do, but that's a good chunk of what we're going to do when we practice these. Second property of the derivative is rate of change. What's a rate of change? Give me an example of a rate of change. Well, 2. What does that represent? The rate of change of what?
It's a slope.
Slope of a line. Rate of change. Rise over run. Okay? Other examples. Go.
MPH.
Miles per hour. Very nice. Good. Also known as?
Rate of change.
Also known as?
Speed driver.
Also?
Slope of line.
Also known as? Velocity. Thank you. Puppies per household. Is that a rate of change?
Yeah, $3 a gallon.
I'm sorry?
$3 a gallon.
$30 a gallon is a rate.
30. So you said 3.
I said 3, but we're good.
We'll go to 30.
Oh yeah,
Okay.
It's a top quality.
Yeah, yes. Super premium deluxe.
It's jet fuel.
Yeah, exactly.
Hydrocarbon max.
Okay, blah, 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 blah. Eventually, we're going to get to word problems. Those word problems are going to involve a lot of different things. Population growth rates. Those are exponential, but we can start figuring out how many people are having children. Production rates. You have a factory and you're making widgets. You produce widgets at a certain rate. How much can you make in a month? Water flow rates. You have a pool in your backyard. You turn the hose on. You know how fast the water's coming out of the hose. How long will it take for the pool to be filled? Can you go and get lunch and come back and not find the pool overflowed? Overflowed? Yeah, that's right.
Flowing.
Overflowing?
Overflowing.
Overflown, right.
Yeah.
Can you find your pool flying in your backyard?
It's floating down the street.
That looks just like our blue. And then velocity acceleration, which is our last of the 3 things that a derivative represents. Slope of a tangent line, rate of change, and a velocity. So now we have a little bit of physics lessons here. If we want to find an object at a certain point in time, that's called the position function. Where is it located when t equals blah, blah, blah? When we take the slope of that position function, which we're actually going to take a derivative of, we end up with the velocity. Do you know the dirt equation? Have you ever heard it referred to as a dirt equation? Distance equals rate times time, or in this form, rate equals distance times time. Rate is velocity. Miles per hour, meters per second. And we're going to start with the average velocity. Okay, so we need to talk about the difference between the average velocity and instantaneous velocity. So picture, if you will, a trip to Grandma's house. You leave your house at noon. You arrive at Grandma's house at 2 p.m. Grandma lives 100 miles away. What is your average velocity? Okay, let's try that again. You leave your house at noon. You arrive at Grandma's house at 2 p.m.
2 p.m.
Grandma lives 100 miles away. What is your average velocity for the trip?
50 miles an hour.
50 miles an hour. Good. Is everybody good with that?
Yeah.
Does that mean that you left your driveway doing 50 miles an hour,
Yeah.
you drove down to every street doing 50 miles an hour, and you came screeching into Grandma's driveway doing 50 miles an hour?
100%, yes.
Yes.
That's why it's 17.
Okay, we're done. Have a nice day. That means that at some point, at 12:30, you stopped for gas. Your velocity was 0. At some point, you realize you're running late, so you jacked it up to about 95 coming down Eisenhower. When everything is said and done, and then you come screeching into Grandma's driveway doing about 35 and a sideways drift, that lands you into the second of her 3-car garages. At some point in time, you're going to have a velocity that's higher than the average. At some point in time, you're going to have a velocity that's lower. And at some point, you're going to have something that is the average velocity. But again, that's an average velocity over the same trip. That is simply the change in distance over the change in time. Okay? That's great. That's exciting. But who cares? I want to know, how fast was I going at 115 when I went flying by that cop? That's an instantaneous velocity. So we're going to compare the two things. So we'll start this. I've got a position function. Okay, now, I'm dropping a billiard ball from 100 feet. And the position function is given by that. Eventually, we'll be calculating those functions on our own, but I'm giving it to you in this case. This is the most frustrating thing for me. When we're solving word problems, I write word problems designed to follow the real world. So, for instance, if I drop a billiard ball from 100 feet up, when you're done, ask yourself a simple question. Does that answer make sense? Is that billiard ball going to be traveling 3 times the speed of light when it hits the ground? No. But I get answers like that. I get answers that make absolutely no sense. Okay, so take some time and do a little bit of analysis before you tell me, well, that's what my calculator said. Calculators lie, kids. Yes, they do. By the way, let's make sure your physics is strong. Let's suppose I jump out of the window.
9.8.
And easy. And Megan jumps at the exact same time.
9.8.
Okay? Who hits the ground first? Same time. That's important to know. The fact that I probably weigh 3 times as much as Megan has no effect. Assuming that we're both either tucked into a ball or like flying squirrels, we're going to hit the ground at the same time. So if I drop a billiard ball and I jump at the same time, we'll both hit the ground. So the object that we're dropping doesn't affect these kind of answers. Okay. I want to know the average velocity of that ball from 1 second, from 1 second to 2 seconds. We'll do part A first. So what do I need to know? Do you know delta T?
Yeah.
What's delta T?
1.
1. Do we know delta S? Can you find it?
Yeah.
Yeah, plug and chug, do it. Tell me what S of 1 is and what S of 2 is.
Oh no, like, that's average.
S of 1 is 84. S of 2.
36.
I hope you did your math right.
Pretty sure.
Adam, like it. What's the average velocity? Change in distance over change in time. What's my change in distance? What is that, 48 feet? Delta S over delta T. 48 over 1 second is, oh wait, 48 feet over negative 1 second gives me negative 48 feet per second. What's the minus sign mean? Going down, correct. We're talking about velocities, and velocities have direction. Forgot the T there. Feet per second. Okay, does that make sense to everybody? Instead of beating a dead horse, let's skip these two and do this one instead. What's the average velocity from 1 to 14 seconds? Calculate that, please. And you will probably need your calculators for this. I erased it. What was S of 1, 84?
Yeah,
84. S of 14,
36. 36.
36?
Oh, I'm thinking about the wrong thing.
No way.
14 squared. Sick.
What's S of 14?
3,036.
Negative 3,036?
Yeah.
Okay, let's stop and talk about that. What does that mean?
It's on the ground.
You're extrapolating.
Very down.
Under.
It's not only on the ground,
In the earth.
it's in the earth. So what happened is, I stood 100 feet in the air and I dropped a billiard ball. According to the math, that ball fell for some time, hit the ground, and then decided to burrow itself 3/4 of a mile into the earth. Does that make any sense whatsoever? No. Calculate the average velocity though and see what you get. Just for giggles, probably not going to make any sense. Negative 3,036 minus 84 over 14 minus 1.
240. Negative.
Negative 240 feet per second. Does that make any sense whatsoever? No. So something's wrong here. What's wrong is the fact that the ball hits the ground and stops moving. Where does it hit the ground? Sorry, wrong question. Right below you would be the answer to that question. The question I meant to ask is, when does it hit the ground? How long does it take for that ball to hit the ground? How long does it take for me to hit the ground when I jump? By the way, do you have any idea, guesstimating about how far you are off the ground right now? We're on the 3rd floor, by the way, in case you got lost on the way up here.
300 feet.
300 feet, that's a good guess. Any others?
like 40 feet.
240
like
feet.
50.
420.
420 feet, good.
55.
Any other guesses?
40 feet.
40. Okay, any others?
40 feet.
40 feet, good. Any others?
68.
68 feet, excellent.
Holy wow.
480 feet.
Oh, that's closest.
Yeah, no. We're about 30 feet off the ground now. Each floor is about 10 feet.
Dang it.
So we're actually probably a little less than that. If I climbed up on the windowsill, I'd probably be about 25 feet off the ground. That's a guesstimate. How could we test how far we are off the ground? Could I use Megan to figure out how high we are off the ground?
Oh, yeah.
Yeah, easy. Throw Megan out the window. Start a timer. Time how long it takes Megan to slide on the ground.
Tell me when you're at the ground.
Do the calculation. We can figure out exactly how far we are. Okay. Those are the kind of calculations we're going to be doing. So what I want to know is, when does this billiard ball hit the ground?
2.5 seconds.
Why?
Because that's when it travels 100 feet down.
That's when it travels 100 feet down.
Yeah, it's not English, but it works.
No, it was English.
Just not.
It's not even math.
I didn't say it wasn't correct either.
Oh, well, I didn't word it right.
When it hits the ground, what's S equal to?
0.
0, okay. Negative 16t squared plus 1 hundo equals 0. Mathematically speaking, that equation has to give me 2 answers.
Yes?
It has to.
Yeah.
But negative 2.5 seconds doesn't make any sense. You're not Marty McFly. You're not going back in time. So we take the answer of positive 2.5 seconds. Okay? So let's do something more interesting. Let's take a diver. Answers, blah, 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 boring. We did this already, great. Slope of the secant line, talked about that. Go here, okay, hold on, wait, I'm getting there. Click, 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 click. Oh, instantaneous velocity. Okay? Let's skip that a second and go to this guy. I've got a guy on a diving platform. He's 32 feet in the air. By the way, I know it's a guy. I'm not being sexist. It's either a guy or a woman with no top. So we'll go with the guy. It makes me more comfortable. There's the position function. As I mentioned, later on, you're going to be putting together your own position function. And some of you that have had physics will understand how that happens. That negative 16 is there for a reason. that 32 is there for a reason. So for instance, if I put in 0 into that function, I get a height of 32 feet. That's where he's starting before he jumps. Okay, then he dives into the water. We've done part A already for the billiard ball, but you should be able to do it for the diver now. When does it hit the water? He, well, it is 2018, it would be better. When do they hit the water? They hit the water when S is equal to 0. Set that equal to solve for T, please. Do that now. T equals 2 and -1. -1 makes no sense, so we get rid of that. It takes 2 seconds for that diver to hit the ground. By the way, did anybody see the video over the weekend from the competition in, I believe it's in Sweden? They have a competition where they put people on top of a diving platform like that, and they dive into a pool, and the goal is to hurt themselves the worst.
Oh yeah, I did see that.
Yeah.
Oh, the body flopping?
They like bleed.
Brutal.
It's insane.
Okay,
No.
we did part A. It hits the water after 2 seconds. Don't forget units here. Now notice part B is different. What's its velocity at impact? Now I'm looking for what's called an instantaneous velocity. At that exact moment that they hit the water, how fast are they going? Okay, so we're going to go back a slide and talk a little bit about instantaneous velocity. Like I was explaining with Grandma, we want to know the time that you were or the speed you were traveling at, let's say 115, not your average velocity, but your instantaneous velocity at a point in time. Okay. That's found by taking the derivative. Now we're past the point of the limit of delta t as delta t approaches 0 of s of t plus delta t minus s of t all over delta t, because we know the tricks for taking derivatives now. And that instantaneous velocity, and all velocities, can be negative, it's going down, 0, it's not moving, or positive, it's going up. The other thing to notice is that speed can never be negative. Do you understand the difference between velocity and speed? Okay. If I get in my car and I put it in reverse and I start flying down the street at 20 miles per hour, my speed is 20 miles an hour. My velocity is negative 20 because I'm going backwards. Same thing is true with that billiard ball that we dropped. When it hits the ground, it's traveling at a certain velocity, which will be negative because it's moving down. Its speed will be positive. The direction doesn't matter. Using this information, we can then solve for the diver's velocity. We know they hit the water when t equals 2. Where do I get the velocity function? Nope. That's average velocity. We want instantaneous velocity.
Change, no, it's distance over time.
Nope.
All velocity.
Now the calculus comes into play. Velocity for us in calculus. Oh, by the way, side note before I forget. Somebody told me that in that other class, physics, you would answer something like feet per second downward. Does that look familiar? No? Good, you never did that? You put a negative in front?
Yes.
Okay, good. Because I've had people answer that way. From a math standpoint, we use negative for down and positive for up. Okay, anyways. Little sidebar there. The derivative of the position function is the velocity function. What's the derivative of the velocity function?
-32t plus 16.
Good. Negative 32t plus 16. So the velocity of this diver at any point in time is negative 32t plus 16. When they hit the water, that's it. 2 seconds. Plug t in there, or plug 2 in there for t, and that person is traveling at negative 48 feet per second. What if I take the derivative of the velocity? In this particular case, I get negative 32. Does anybody know the significance of that number, negative 32?
Distance
That's a
travel?
starting point?
Nope.
That when t.
No, it just happens to be a fluke in this problem. It doesn't always work out that way. Due to gravity. Yes, it is the acceleration. The derivative of the velocity is the acceleration, and in this particular case, it's the acceleration due to gravity. So v prime of t is equal to the acceleration, which in this case is negative 32 feet per second squared, which is, you probably use negative 9.8 meters per second squared, right? I don't know if you do anything with feet per second in physics, but we switch it up in math. Okay? So again, when you're done with these problems, ask yourself if your answer makes sense. If you get an answer like 48 feet per second, you've done something wrong. That means the diver jumped off the diving board and flew up into the air, which would be really awesome to watch, but not possible. Unless the diver happens to be Superman. But not Batman. But not Batman, because he has no powers. He's just a human.
It's a lot of money.
A lot of money.
That's why I know rich people have superpowers.
Yeah, we did this already. Yeah. 1 and 2, we did that. Okay, then got that. Oh, yeah, and then put it into negative 4. Yeah, okay. That should actually say day 24. I screwed up.
Yes.
Okay. We're going to spend at least 2 more days in this section because it is so incredibly important. So you have day 23 from Friday, day 24 for tonight. Now, after grading your tests, I started to realize a fairly common problem that's popping up, and this is on you. I assign problems based on things that I know are important to cover. My assumption is that if you don't ask, you had no problems with it. I saw a number of problems on the test that were just like homework problems that people had no clue to do, or how to do. Which means that at some point when you're doing your homework, you stumbled on those problems, and you never asked, who's that on? That's on you. Right. Grassy, that's right, I forgot, we blamed Grassy for everything. So as you dive into these homework problems, you have to be more aggressive on more of these problems. I don't get problem 16, how do we do it? Okay, I'm done ranting. The other thing, you should all have the quadratic program, you should all have a distance program on your calculator. If you don't, I would be happy to share those with you. Okay, that way you're going to save yourself a lot of trouble. All right.
Yeah.